All right. Hello, everybody. Thank you for joining us today. My name is Aisha, and I am one of your Solid State Circuit Society staff members. The topic of today's webinar is the dawn of AI revolution in chip design. Today's webinar will be a little over an hour, and we will hold a Q&A session after the webinar. Attendees of this webinar have the opportunity to earn a certificate of participation for attending this webinar. I will put a link in the chat box with instructions on how to obtain the certificate, and the webinar video will be posted on the SSCS YouTube channel after the webinar. Please use the Q&A on your dashboard to ask any questions. I will now open it up for a few welcoming remarks.
Hello and welcome. My name is Xiyuan Tang, and I'm currently an assistant professor at Peking University, and also an IEEE SSCS Young Professionals Committee member. I will be the moderator for this webinar. It's a great honor for us to have Dr. Mark Ren from NVIDIA Research here with us. Before we kick off this webinar, I will start with a short introduction of who we are and what we do. As young professionals and students, you make up more than 30% of our overall membership, and you are the future of IEEE SSCS. As the SSCS Young Professional Committee, we strive to address the different needs and interests of our younger members with initiatives like this webinar today. Here presents some selected benefits of the SSCS membership for young professional members. You will have access to the SSCS Resource Center, which contains technical tutorials, short courses, and webinars. You will have the distinguished lectures in your local setting, and there are opportunities to apply for various grants and awards. And you will be able to develop leadership skills and make professional connections by becoming a local or global young professional leader. We also have this SSCS young professional networking event at top conferences. In addition, we have this new online mentoring platform. It helps you connect with mentors around the world virtually. Here covers some activities that our committees has worked on. We had the young professionals and the women in circuits mentoring event as a part of VRSI at Hawaii, and the ASIC mentoring event at Milan. The upcoming event would be hosted in SSCC in Taipei this year. The mentoring event includes panel and breakout sessions where multiple topics will be discussed. It will be open to all SSCS members and ASSCC attendees. So please go to the website to check more. We have hosted webinars for Young Excellence, which is a quarterly webinar series to young professional members, and the list we did in the past is shown here, and all the webinars are available at SSCS YouTube channel. So today we bring you the webinar, The Dawn of AI Revolution in Chip Design. So let me first briefly introduce our speaker, Dr. Mark Ren. Dr. Ren leads the Design Automation Research Group at NVIDIA Research, and his research interests focus on AI and GPU acceleration for the EDA. He also spent 15 years working at IBM Microelectronics and IBM Research developing internal EDA tools and methodologies. He is widely recognized for his leading work in physical design and AI for EDA, and has received multiple awards, including IBM Corporate Award and Best Paper Awards at ISPD, DEC, and TCAT. He is a graduate from Shanghai Jiao Tong University and earned his PhD from UT Austin. And if you have any questions during the webinar, you may leave it in the Q&A box. We will address them at the end of this webinar. So without further ado, let's welcome Dr. Ren.
Mark, you should be able to present now.
See my screen?
Nope, not yet.
I'm sharing. Oh, just a second. How about now?
Yep.
All right. Thank you. Thanks, Xuan, for the introduction, and thanks for inviting me to give this talk. I'm very glad to talk about this very exciting topic, using AI for chip design. So my talk has 6 sections. I'll start with a general introduction of AI, and then I'll talk about my personal journey of discovering AI from the EDA background. Then I'll talk about how can AI help chip design from the design methodology perspective, followed by a discussion of commonly used AI usage models for chip design. Then I'll use a design application as an example to illustrate these usage models. Then I'll look into the future and talk about important design challenges for AI to address, and also the address of the challenges of adopting AI, and some predictions on what the chip designer jobs will look like in the future, and give some advice for the young chip design professionals. So let's get started. An AI revolution is happening today. Just like the previous revolutions in the human history, we have revolutions of transformations of material from Stone Age to Bronze Age to Iron Age, and then revolution of transformation of energies, right, from water, steam power, electrical and combustion powers. Then in the last century, we have the communication revolutions and then the computation revolutions. Now you can see the difference between this latest computation revolutions with the previous revolutions are previously they all stabilized after a while, but we expect this computation and the information age revolution to continue to speed up, and that's because the adoption of the artificial intelligence AI in almost all human activities. So what is the core of the AI? Let's talk about the main part, which is deep learning for the AI. So deep learning is about the functional approximation of given inputs and outputs using neural networks. This approximation is formulated as a loss optimization problem. Basically, you can see that given the input x, here that the x is the image of a cat, this input x goes through a neural network parameterized by network weights w, which compute a function g that produce the output y, given x. We also give the desired output y, which is what the function g tries to approximate. So the function is trying to minimize the loss, which is the difference between the function g generated by y and the desired output y. And then this can be minimized with gradient descent methods. So for neural networks, it is also called back propagation. It's basically gradient descent. So you can see that the process of gradient descent happening in this middle plot, the middle figure. It shows the space of the network weights and the different gradient descent algorithms trying to find the optimal weight point to optimize the function loss. And there are a lot of innovations on the structure of this network, the G function. For example, the Google LearnNet was one of the earliest structural innovations. And also there's a lot of innovation on how to create this object optimization objective, which is the loss function. So why AI is useful? I think there are 3 main usages that make AI very useful. One is prediction, second is reasoning, and the third is imagination. What is prediction? Prediction is basically given some inputs, you can predict the output. So for example, Google's AlphaFold work that can predict the protein 3D structures from its genome sequence. The second one is reasoning. It's planning for or optimization of the actions of agent. So a well-known example is AlphaGo. It can play the Go game as good as or better than any human beings. And the third is imagination, which is the generation of new data from existing data distribution. either conditionally or unconditionally. So the latest example is the Dell E2 model that can take in a text description and generate an image. Okay, so let's talk about my personal journey in discovering AI. So my background is in EDA, and I did a lot of physical design and synthesis work while I was at IBM. So one of my favorite EDA topic is placement. So after I joined NVIDIA, I tried to look into how to use GPU to accelerate placement, and then I discovered that placement optimization can be formulated as neural network training problem, which leads to me to study artificial intelligence, and then I start my AI journey. So here's the placement problem. The state-of-the-art placement algorithm is called the nonlinear placement algorithm. It basically tries to minimize the function, this particular function, which has two terms, the wireless term and the overlap term. So the wireless represent total wireless of all the cells and blocks, and then the overflow term represent the overlaps between those cells and blocks. So we need the overlap term because we don't allow cells and blocks to overlap each other. And these terms are determined by the position of the cells and blocks. And these positions are expressed as variables x and y. For this nonlinear optimization problem, the standard algorithm is gradient descent. As shown in the animation, the location of each box and cells are changed by the gradient descent algorithm during optimization. So this is very similar to what the neural network is trying to solve, which is to minimize a particular loss function given the weights W and the data X. So I realized the similarity between the placement problem and the neural network problem. They both use gradient descent algorithm to minimize some objective. So that's why I'm looking into how to use deep learning framework such as TensorFlow or PyTorch to solve the placement problem. Because these frameworks provide mechanisms to compute the functional gradients efficiently. They also provide utilities to help the scale these algorithms to run on multiple CPU and GPUs. So if we formulate the placement algorithms as a computational graph in terms of tensor operations in deep learning framework, then we can express the placement objective as a loss function and be able to use this automatic gradient methods computed by the framework to optimize it. So even sometimes the default tensor operations are not efficient enough because the placement problem has a lot of sparsity. We can still design a custom CUDA kernels to implement these operations directly on CPU. And another very good benefit of using these deep learning frameworks are the development efficiency. So instead of writing C++ code, we only need to write Python code, which is easy to write and maintain. And this leads to one of the first work in doing the GPU-based placement using TensorFlow. And that work was published at the GTC, which is the GPU Technology Conference in 2018. And later we collaborate with UT Austin to further implement a state-of-the-art placer algorithm on GPU, and we call it GenPlace. So it is able to speed up the placement by 40, 50x with the same quality results as a CPU-based placement, and received best papers awards. Okay, so let's switch gear to talk about the next topic, which is how does AI help chip design? I want to answer this question from a unique perspective, the design methodology perspective. So this perspective helps us see the big picture more clearly and systematically. Modern chip design process is very structured. The design activities are based on design methodologies, or sometimes called the design flows. For digital design, a design methodology might include architectural design, RTL design, physical design. For analog design, a methodology might include schematic design, layout design, and simulation. These design methodologies are hierarchical as well. For physical design itself, it can also have many different stages, such as synthesis, placement, optimization, routing. So we can define a methodology as multiple steps and a flow that connecting these steps. With this perspective, let's look at how AI can help. The end goal of any design methodology is trying to improve the chip design quality of results. In short, is the QOR. as well as design productivity. So given this perspective of multiple steps and the flow, we can see there are at least 5 major ways that AI can help. First, it can bridge the gap between the steps, and then it can do better optimization for each step. And in addition to optimize for each step, it can optimize for the entire flow. It can also speed up each step. And finally, it can automate some of the manual steps. Now, let's take a look at some details. Now, for the bridging gap between steps, design steps often have dependency to each other, but these dependencies are difficult to estimate. For example, in analog design flow, the schematic design depends on the layout parasitics estimation. This parasitics has significant impact to the performance of the circuit and cannot be estimated accurately at the schematic design stage. A feedback loop from layout design to the schematic design is quite long because it takes a very long time to do the layout design. So if we can predict what's going to happen in the layout, then we can reduce the iteration loop. For example, here, there's a all-pan schematic design, and there's a bunch of parasitics associated with the circuits. And these parasitics can only be extracted from layout with the existing design methodology. Now, using AI, for example, using the graph neural networks, we can predict these parasitics given this schematic graph trained with the existing layout data. This is doable because we may have multiple designs using similar circuits, and we can train this model, learn from those data, which will significantly speed up the schematic design process. The second way is improving the chip design if we can do a better optimization for each step. So in this example, this is a macro placement step. This is the macro placement is a part of the physical design flow. And because macros are larger blocks of IPs that usually placed first to anchor the standard cell placement. There's a recent research from Google formulates this macro placement problem as a reinforcement learning problem. The action of the agent is to place one macro at a time, and then the reward at agent are the total violence and the congestion estimation after all macros are placed. So this animation also shows the agent in placing the macros during training. They claim that produce the better macro placement than manual macro placement or even some EDA tools. The third way is to better optimize the entire flow. Instead of just one step at a time, AI can be used to optimize the whole flow, usually by adjusting 2 parameters as well as design inputs and constraints. This is perhaps the most successful use of AI in EDA currently. Commercial EDA companies have developed their own EDA tools to do AI tools to do this. For example, Cadence has this tool called Cerebrus that can tune the 2 parameters of their Genesis and Innovus flows, and as well as design constraints and library operations together. The fourth way of improving chip design using AI is to use AI to speed up a design step. Sometimes a design step is very computational extensive, taking hours or days runtime, which delay the flow and make design analysis and exploration limited. If we can speed that up, then that'll be great. So for example, the IR job analysis, because it needs to analyze many different design vectors and solve large number of numerical equations, it is often very slow, taking hours of runtime, and often it cannot simulate enough input patterns. So we can use machine learning model to predict the IR job given input vectors. It will be much more efficient, and we can analyze a lot more input patterns. As you can see in this work, it can be done actually. Compared to the ground truth IR image, the prediction accuracy is quite high. And the last but most importantly, we can use AI to automate the manual steps in the design methodology. Many design steps are still manually done today, like this example, standard cell layout design. If we can use AI to automate these steps, of course, it will increase our design productivity. And in this example, it shows how AI can automatically generate the cell layout for a given standard cell. All right, now let's talk about common AI usage models. Just like I mentioned earlier, there are 3 ways to apply AI: prediction, reasoning, and imagination. In the chip design domain, we also call reasoning as optimization and imagination as generation. So for prediction usage model, usually AI is used to predict some design output data given some design input data. This task is often done with supervised learning models. For optimization usage model, usually AI is applied to change some design data in order to optimize some design cost function. It can be done with either model-based hyperparameter optimization methods or reinforcement learning. For the generation usage model, AI is used to directly generate design data, sometimes conditioned on some given design data. These AI models are often trained with self-supervised learning methods. So to illustrate how this usage model works, instead of giving different application examples for different usage models, I decided to demonstrate most of the usage models with one application, which is the standard cell layout automation. Let's take a look. So what is standard cell? Standard cells are cells like NAND gates, NOR gates, adders. These are building blocks for modern digital design. Standard cells are organized in cell libraries, and each library could have more than 1,000 cells. The performance of these cell designs have a big impact on the final chip product. It affects the performance as well as the cost of the final chips. Because of the importance, it usually takes design team months to design each library. So when you have a very efficient automatic layout tools, then you can have a much faster turnaround time and improves the productivity. You can also explore a lot more design space of the cell design, which improves the performance, and you can do a lot of custom cell designs to improve the circuits. And finally, you can do design technological optimization, DTCO, if you have good cell layout cell design tools. So here's the basic flow of cell layout design. It shows the automation process for 3 input NAND gates. Then starting from the schematic of NAND gates, then it will be generate the layout of the gates represented by a simplified grid-based layout diagram. This layout diagram can be directly converted into a final layout. In addition to represent the layout, this grid-based layout diagram can also be used to express the check the DRC errors. There are two major steps in automation the cell layout: placement and routing. The placement step places transistors. As you can see in this picture, it places 6 transistors on 2 rows, 1 for PMOS and 1 for NMOS. And there are many algorithms to do placement previously, but the key difficulty is to predict the routability, because some placement is not good for routing. So we have to make sure the placement generates routable designs while optimizing for minimal cell area. This is the opportunity to use the prediction-based AI usage model, which we'll explain later. After placement, it needs to route wires to connect these placed transistors, which are shown as the blue and the black wires between the transistor. Again, many algorithms have been proposed before, but the key problem is to solve a growing number of DRC rules, because there are a lot of DRCs rules on these lower level metals in advanced technology nodes. This is an opportunity to apply optimization-based AI models, such as reinforcement learning. And finally, the entire placement and the routing flow can be further optimized. This is another opportunity to apply the optimization-based AI models, particularly this model-based parameter tuning methods. So let's look at some detail. First is the routability prediction during placement. Essentially, the placement engine will place multiple transistors on 2 rows, as shown in the top left figure. Here, a number present represent a placed transistor. It will also place the input pins and output pins of the circuits. This figure, it is A, B, C. These are pins. And two transistors on top of each other forms a column. And we use a P1, P2, P3, P4, P5 to label these columns. And each column will have one PMOS and NMOS transistor. The goal of routability prediction is to predict whether a given placement is routable. First, we collect the features from each placement column. And these features would include numbers such as number of gates terminals, number of pins on the left, and number of pins on the right, a number of nets crossing the column, and whether diffusion on the left or right of the PMOS and NMOS transistors are connected. So we can collect a bunch of features for each column. And then we can concatenate these features on all columns together to construct a vector, a vector feature. And then this can go through a 1D convolution layer and do a maximum pooling and finally predict the routability of the entire circuit. So this kind of predicting model is very efficient, and we actually train the model and see a 94% accuracy in predicting the routability. So using these predicting models in placement engine, we can achieve 5% additional overall success in layouts. Now let's talk about some detail about routing. Here's the diagram of the routing flow. We use the conventional algorithms such as genetic algorithm and maze routing to generate many candidate routes, but they left unfixed DRCs. So how do we reduce the number of DRC? We leverage reinforcement learning agent to fix those DRCs. This agent will fix DRC as much as it can, and the remaining DRCs will be feedback to the genetic algorithm, which will try to optimize the number of DRCs by rearrange their chromosomes for the router. And then we would redo the maze routing and generate new candidate routes, and then run the DRC fixing again using reinforcement learning agent. So what does the reinforcement learning agent learn to fix DRC? Basically, we have to formulate the DRC fixing problem as a game. You can see that in the beginning, there's one wire here, and there's 6 DRCs indicated by the red crosses. The agent learns to add additional metals on the existing routes. It adds one metal at a time, and the DRCs are re-evaluated after each step. At the end, the DRCs are reduced to 0. So basically, the agent will see the existing routes as its observations and then compute actions for the next step to inject additional routes. And the reward is the number of DRCs reduced at each step. And this animation shows the examples how the DRC is fixed during this game on a medium-sized standard cell. In the beginning, there's like 27 DRCs, and at each step, the agent insert a new route, which will normally reduce the number of DRCs. Sometimes the DRC number would actually increase after step, but overall, the total number of DRCs are reduced because the agent objective is to optimize the total reward, not just the reward after each step. And all DRCs are fixed at the end of the game. Another very important usage model of AI is hyperparameter optimization. In the cell layout automation example, the placement routing algorithms depend on many parameters. For example, there are weights associated with each design objectives. And there are also hyperparameters for placement simulating a linear algorithm as well as the routing genetic algorithms. Different parameters will result in different results on each cell. Now, what's the best set of parameters for a particular cell? That's unknown. So essentially, we try to search for the best parameter. And this search process can be based on a model trained with AI. And we're building a model to predict which parameter is the best for a particular problem. And this can be done with Bayesian optimization. Shown in the right figure, Bayesian optimization is basically responsible to sample new data points, in our case, new parameters. And based on an internal model trained with prior data point, it will predict how likely a new design point would find a better optimal than the existing one. And the Bayesian optimization is particularly advantageous for problems where the objective function is difficult to evaluate due to computational cost. And the problem usually has less than 20 dimensions. So this, as a result of using Bayesian optimization, there's another 5% of improvement over the baseline. So this standard layout cell layout tools we call the NV cell. It applied all three AI usage models I mentioned earlier, and has been used within NVIDIA to design all our new standard cell libraries. Here we show a direct usage of NV cell on our latest standard cell library. We see that NV cell is able to produce 92% of the cells with DRC and LVS clean layout. And more importantly, compared to manual design library, it's often smaller, which is better because the smaller the cell, the better the cost and the performance of the chip. And the key benefits of automatic layout design flow is not on the direct application of NV cell, but on its impact to the design methodology. So let's take a look. What's the impact? If you look at the cell design methodology, there are three major steps: schematic design, and then layout design, and then evaluation of the layout design. And then they redo the schematic design. So there are multiple iterations in this loop. Now, the main problem here is that in the industrial design setup, schematic designs and layout designs are usually done by different teams. The layout design is done manually, and the communication between the schematic design and layout design teams, here we use a dotted arrow because they are different teams and they might have some communication delays. And that's why this iteration loop usually takes days to accomplish, including the delays of communication as well as the manual layout design time. Now let's look at the new design methodology enabled by NV cell. The manual layout design is out of the loop. We can just use NV cell to implement the layout. So this loop becomes much faster. It only takes hours. And in addition to that, the designer can design multiple cells at this time. And that's why we use a thicker arrow in this loop. And this can significantly increase the design search space, which leads to better design quality at the end. With this flow, we conservatively estimate at least 50% improvement in productivity over the entire design cycle of library design. In the previous cell layout application example, we introduced these two main AI usage models, like prediction and optimization, and the two different optimization methods. Now, let's talk about the third usage model, which is the generation or imagination usage model. This is actually a very exciting usage model for AI. So let's show you two examples. One is the automatic buffer generation method. This work will be published at ASPDAC next year. It solves this buffering problem. Given a net with a source and multiple sinks, and each sink has its required delay from the source, the AI model learns to generate a buffer tree based on self-supervised learning for a very large number of optimized buffer tree data. And another very interesting example is the RTL code generation problem. So given a verbal description of the function for the RTL, the model can learn to generate the actual RTL code, implement that function. This is trained with large language models such as GPT-2. Although it's still very far from practical use, but very exciting directions. Now let's look into the future. I will illustrate several key chip design challenges and describe how AI can help solve these challenges. So the first challenge is verification. As coded in this article, verification consumes more time resources than design, and yet little headway is being made to optimize it. In former Mentor CEO Dr. Ryan's DVCon 16 keynotes, he also showed that from 2007 to 2014, number of design engineers only increased 3.7%, but the verification engineers increased 12.8% per year. And this trend will continue even today. Verification definitely these days spend more than half of the total design resources. And so it's a big problem for AI to help. AI can help verification in multiple ways. It can accelerate the coverage closure. Functional verification is usually driven by functional coverage. AI can help speed up this coverage process by either predicting coverage numbers of a stimulus without simulating it, or come up with better test bench parameters to improve the coverage. Verification can also be AI can also be used to accelerate formal verification tools. The process of formal verification algorithm can be improved with data-driven decisions made by AI. And finally, debug activities is a major activity in verification. AI can help bug localization, in other words, pinpoint which line of the code could potentially cause the bug, as well as anomaly detections to identify problematic traces from long trace of simulations. The second challenge is analog design automation. Compared to digital design, analog design productivity is like in Stone Age. As quoted in this article by Schutable and Linick in ISPD 2015, physical analog IC design has not been automated to the same degree as digital IC designs. This main issue is the design constraints are not well specified for analog design as those in digital designs. In digital design, each design stage has clear boundaries of design constraints, therefore has clear boundaries of reduction of the degree of freedom. While in analog design, the constraints are often implicitly defined, maybe based on designer's experience. So these constraints are dynamic and contradictory and complicated. So how can AI help? For analog layout automation, we have seen AI being used in extracting and generating constraints automatically, and also used to optimize layout given its constraints. Both University of Austin and the University of Minnesota and NVIDIA have done works in this area. AI can also be used to generate and optimize analog circuits. The parasitic prediction work I mentioned earlier belongs to this category, and additional directions can be used. Can use AI to speed up analog simulations or help improving analog verification. The third challenge is design tool capacity, as indicated by Samir Halevs in his ISPD 22 keynotes. The average size of design levels off, but unique blocks count skyrockets. This can be seen in this plot. Though recent years, the number of design blocks increased significantly. I think it's like 30% year over year. And the reason is because the block size of each design block kind of levels off, because the design tool can no longer support a larger block size efficiently. For example, a 2 million cell blocks might need 7 days to run the entire physical design flow. And the reason that because the computation capacity of this tool is limited, they cannot effectively leverage large number of parallel computing resources available in the modern hardware. Even if we give those tools more cores, more CPU cores, the additional speed up is very marginal. That's why we have to limit the design block size. But when you increase the design overall transistor count, then the design block size increase as well. The number of design blocks has a significant impact on the number of designers, as well as computational resource and the EDA licenses. So that's a scalability challenge. So how can AI help? We can create scalable physical design tools based on GPU acceleration and AI algorithms. For example, the GPU accelerated placement problem is one way to speed up the process. We also demonstrate that optimization problems such as gate sizing and buffering can be solved with generative models as optimally as conventional algorithms, but much faster, like 1,000 times faster. So number 4 challenges is system integration. Here's a quote from Mark Liu from TSMC in his ISSCC 21 keynotes, that the future is the integration. is the system integration. And we're going to have 3D designs, chiplet-based designs, different kind of logic memory integrations. And on top of that, there's architecture software integrations. So the future is to optimize all those design choices end to end, from software all the way to device technology level. So how can AI help? First, because now the design space is so large, AI could help improve design space exploration efficiently. Because there are so many stages in the flow, predictive models or some sort of fast implementation will be very helpful to make decisions at early stage. And of course, an end-to-end optimization can be done with AI too. So we have discussed the benefit of AI for chip design, but the revolution has not yet fully happened. Why? There are challenges for AI to revolutionize chip design. I think there are 3 challenges. First, AI is very useful for image generations, but chip design data are different. There are structural data such as netlist and circuit graphs. So we haven't seen like very significant breakthroughs in this structural graph understanding using AI. So graph neural networks have been proposed to be the CNN replacement of the graph. But there are still a lot of open research questions. So, and the second challenge is the data set for chip design. The data set is a key component of AI model training. The issue of data sets is that it's not just the availability of open source designs that you can create the data sets, but also the coverage of different design styles, different design metrics, and what's the optimality of your design data sets. So we are glad to see some open source design data sets published recently. The third challenge is the lack of killer applications. The killer applications in AI, such as AlphaGo or AlphaGo or DAL-E, similar killer applications in chip design domain can certainly accelerate the adoption of AI in chip design. And finally, the production of AI technologies. AI surely will not solve every single chip design problem. Therefore, we must continue use some traditional design tools. Then the challenge is how to integrate the AI-based tools with those traditional tools. And also the design infrastructure today was not designed with AI in mind. And the server farms today don't have many GPUs. And in the future, we're going to see GPUs to be integrated into design server farms or at the cloud. Nevertheless, I believe AI will eventually revolutionize how people design chips and will have significant impact to the job of design engineers. I think the main impact will be the design abstraction level. In my opinion, many low-level design problems can be solved with AI-based prediction, optimization, and generation. So designer will move more and more to a higher level of abstraction than today at the RTL level. So they will probably optimize architectural designs along with system softwares without thinking too much on how RTL will be implemented or optimized. And recent trend in software hardware co-optimization of AI accelerators has shown some early signs of this direction. So, and this has a big indication for the future because the designers' skill set will change. I think the designers would become kind of like a data scientist because they will be capable of making design decisions based on the data. Also, designers will become like design automation engineers or vice versa. And not just because of the AI revolution. I have seen many good designers actually decided to do design automation tools because they can do so to impact design more broadly. AI actually gives designers a good opportunity to become design automation experts because AI is much more powerful and do not rely on complicated EDA infrastructures than the normal tools. Okay, now my advice for young professionals, I think everything goes to fundamental, right, and the principles. And so we need to understand what is the AI principles, EDA principles, and design principles. So good understanding of principles in these domains are very important. And because AI is developing very fast, so you have to keep up with the latest AI trend. That means you have to take online classes or watch tutorials, read the latest papers, attend conference. Just keep yourself updated with what's happening out there. So once you have the fundamentals, then we'll try apply AI in your own design problems. And the key is you want to be brave to allow yourself to dream about different solutions to the problem using AI methods. And in the meantime, you have to follow the first principle. It cannot be an analogy kind of solution. So the difference between the first principle and analogy is the solution based on first principle. Look at the physical reasoning and the laws of the problem instead of just an analogy from a method in some other domain. For example, just because CNN solves the image recognition problem does not mean it should be used in physical design unless there are some underpinning principles that warrant its success. And then finally, always strive for end-to-end solutions, because if you only solve part of the problem, then the results might not be as good, and you probably have to rethink the whole process. Okay, so at the end, I want to leave you with this thought. So currently, designers design chips, and these chips will be used to train AI models, and more and better models will be trained with larger and better chips. So you have this edge from the chip to AI, and that's a positive change. Now the other way, which is where you have a strong AI, and how can this AI help the chip design process? Currently, this loop is not closed. That's why I use a dotted line here, right? So if we can make this backwards process happen, then we're gonna have a loop, right? This loop basically means the better the AI model, the better the chip, and then better chip, the better the AI model. So that's a positive feedback loop. Will significantly accelerate. As shown in the right figure, the evolution of artificial intelligence might look like this picture. It might only be kind of a very low intelligence at this point, maybe just like ants or birds today. But the people, I think this evolution will accelerate it quickly, right, to the level of chimps or dumb human or even smartest human. In other words, to achieving the artificial general intelligence, right, AGI, which is the holy grail of AI. So how can this happen? I believe that this feedback loop formed between chip design and AI will not only revolutionize how chips are designed today, but also help realize this accelerated AI evolution and AGI sooner. So that's the end of my talk. Thanks for your attention.
Well, thank you for your wonderful and insightful talk and all the useful comments. And it's also very exciting to witness all those progresses. Now we will start the audience Q&A session. As a reminder for our audience, please use the Q&A section on your dashboard to ask any questions. So we have a few questions coming in already. Like people is asking, what is the training data set and how do you obtain that for the AI training? And how to make the connections among different EDA tools?
So this has to be analyzed case by case. So it's a data set. Data set collection is always the first step for any AI project. Right. This is unlike the AI for other domains, which you usually have a lot of data sets. But for AI for chip design, most likely you will have to collect your own data sets for your own design problems. So currently, you can look at the design collaterals, such as netlist, timing, timing reports. So these are files that you can access to extract information, extract data from those collaterals, or you can use some open source tools to generate new design data. Some commercial tool can also give you more data. Yeah, so it's depend on what problem you're trying to solve, and then you figure out what kind of data sets you need.
Okay, thanks for that. And people are asking like for the analog circuit design automation with AI, and you mentioned the biggest issue is it's very difficult to define the design constraints, right? So how can the circuit designers help to design the design constraints? Like what are the useful sort of processes to find out the implicit constraints you mentioned?
So traditionally, yeah, people have come with different methods to extracting the design constraints, and some based on graph analysis, and similarities, and some based on the layout, right? So you can actually look at the actual layout of previous design and trying to extract constraints from those layouts. So that's what's been done today. But I think in the future, this constraint process will be more sophisticated with additional AI.
I see. So the constraints you mentioned are symmetry and what else? For the analog circuits.
Symmetry is definitely one of the most important constraints, right? And but they are basically placement and routing constraints. If you think about layout, it's basically place and routes. So there are additional constraints as well.
I see. And we are always saying kind of analog RF circuits are kind of fully customized, right? Because they are super sensitive. Like based on your vision, although you touched a little bit, like how big of a role AI or machine learning will play in designing analog or RF circuits, like maybe in the future?
I'm sorry, can you repeat the question?
Oh, yeah. So based on your vision, like how big of a role AI or machine learning will play in designing analog or RF circuits?
How big the role? Okay. Well, currently, I think we are at the, I mean, that's why we are at the dawn, right? So it's a very limited usage currently, right? But I think we're going to see more. We easily will see more adoption of AI in many different areas of analog design, including layout generation as well as circuit optimization, and so basically the design itself. So the holy grail problem is let's say you just want some design metrics, right? And then how do you come up with the right circuit, the right layout to achieve that design metrics verified by simulation? So that entire process is end to end, and the complexity of analog design, like if you look at the number of devices, usually not that high. So it is possible to accelerate, to do this whole thing end to end. So layout design just part of the process, right? Because at the end of the day, what you really cared about is the QOR, is the design metrics, right? Which you can evaluate. So if you treated the whole thing as a black box, then one day, like AI can probably do the whole thing for you.
Okay, okay, thanks for that. And in the advanced technology nodes, there are many design rules that are very hard to fix, even with human efforts, right? How would AI overcome those in general?
We talk about design rules, or
Yeah, the
okay.
design rules.
Is the question about the cell design?
Yeah.
Okay. Yeah. So let's see.
Like especially in the advanced technology nodes, right? The design rules are so complicated.
Right. That's why we use reinforcement learning, right? So it's so first of all, we can evaluate all the DRCs. So given a particular layout, we can evaluate DRC. That's no problem, right? Because we have tools to optimize to evaluate that. So we train an agent to modify the design such that it will fix as many DRCs as possible. So the reward for that agent is the number of DRCs it fixed in total. So in this case, it fixed 3 rewards. We give us a reward of 3. Sorry, the total reward is 6 because in the beginning there's 6 DRCs, but at different steps it fixes some DRCs and you get some rewards. But reinforcement learning trying to optimize the total reward. So total reward you get is 6, right? So it's not enough. Yes, it's possible that given the initial design, you cannot fix all of them, right? That's totally possible. However, we use this as part of the optimization loop. So in this loop, the DRC fixing is just one step. We have other steps that are actually trying to generate the design candidates. So even though the RL agent for each particular candidate, you might not be able to fix everything, but now we can generate more and more candidates and they're trying to optimize the number of unfixed DRCs.
I see.
So at the end, you will see DRC-free routes. Of course, the whole process is also not guaranteed. That's why we report like with different methods, we're increasing the success rate, right? So it's still not 100%, but we can keep improving. And a lot of time you can actually by manually fixing 1 or 2 things, then the resulting layout is actually complete. So yeah.
Oh, okay. Thanks for that. And the next question asks, could you provide some insight on the quality of AI solutions based on initial values, especially as the solution is non-deterministic? For example, in placement, should we provide the pin locations as a starting point?
Yes. So the quality of solution is quite good. Because it's a search process, right? So you can generate many candidates. We can easily generate many different potential good quality layouts, and yeah, it's a design team can just take a look and be able to pick the best they want. It's much faster than coming up with manual design one at a time. So yeah, there are things that the design team will look on their own. They have their own judgment criteria. But in general, we produce the AI tool produce very good quality solutions.
Okay, thanks so much. And due to the time limitation, I think that's all for the audience Q&A part. And again, on behalf of the committee, I would like to thank Dr. Ren for sharing your insights and perspectives on the relationship between AI and the chip design. And thank you. So I think that concludes today's webinar.
Thanks.